Hey everybody, welcome to the Energy, Frequency, and Wavelength lecture. Let's just go ahead and jump right in. Get us going as quickly as possible. All right, so my first question is, where do colors come from when you see a rainbow after a rainstorm? They're usually in the same order. They're considered to be known as Roy G. Biv, right? Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. So the colors form due to how radiant energy or sunlight interacts with matter or raindrops. So our radiant energy is sunlight and our matter is raindrops. Now, Sir Isaac Newton discovered that when light passes through a prism, it separates into its component colors. Now, he showed how the colors could be recombined into white sunlight with the second prism, and he proved that white light is a blend of all the colors in the rainbow. It wasn't until centuries later that scientists would realize that when light, which was emitted by elements, particularly group 1 and group 2 elements, they are vaporized and their atoms are heated by flames, when their atoms are heated by flames. So that produced light that consisted of only a few bright lines on a dark background. Now, such experiments employing light sources showed that element on the periodic table emits a characteristic line spectrum when its atoms are heated to a sufficiently high temperature. Now, just to be clear, radiant energy is characterized by two variables: wavelength, which is denoted by the lambda sign, and frequency. A wave is nothing more than just a simple oscillation or a periodic movement. That's what oscillation means, that can transport energy from one point in space to another. Some common examples of waves are all around us in our everyday lives. So if you go to the gym and you're shaking the ropes, you're shaking the end of a rope and it transfers energy from your hand to the other end of the rope. If you're skipping rocks, or maybe you drop a rock or a pebble into a pond, causes waves to ripple outward along the water surface. And then, of course, expansion of air that accompanies a lightning strike generates sound waves, which we understand as thunder, and they can travel outward for several miles. So just to show you, I wanted to show you how everything is represented when you're working on your energy, frequency, wavelength, and electron configuration worksheets. I want you to know what you're working with. So your wavelength, which is measured in meters, is going to be represented by a lambda, and your lambda is right there on your left. This is going to be a lambda, okay? So then you have frequency, which is measured in seconds, and that's going to be represented by this. It looks like a V. It's not a V. It's a Greek letter, okay? And then, of course, your C is your speed for light for these particular problems, 3.00 times 10 to the 8 meters per second. Now, this is just a handy tool for you to have so you know what you're working with. You see the word wavelength, you know you're working with lambda. You see the word frequency, you know you're working with your little V-looking Greek letter. And then if you look down to the lower left, you're going to see a formula. You're going to use that formula, and because of algebra, you're able to move things around inside that formula that should get you pretty much where you need to be when we're looking at that. So just to show you how to read the wavelength. Now, radiation composed of a single wavelength is termed monochromatic. Single, mono, one, okay? When radiation from a source such as the sun or other stars is separated into its components, a spectrum is produced. And that's what you see here. So this is your frequency spectrum. This separation of radiations of differing wavelengths can be achieved by passing the radiation through a prism, okay, through a prism. Now, just to show you again, we have some more variables that I want to make sure you guys are aware of. Your capital E is your energy. Your H, your capital H, is your Planck's constant. You might see it as a lowercase h. And the Planck's constant is going to be 6.626 times 10 to the negative 34 joules per second. And if you look at the lower left, you're going to see a formula you're going to be able to use. And again, thanks to algebra, laws of algebra, you can move that formula around to get to where you need to be to figure out your questions that are coming up. So we are looking at a spectrum, right? So we're looking at lowest to highest, lowest on the left, highest on the right. Now, a particular source of radiation energy may emit a single wavelength, as in a light emitted from a laser, or different or many different wavelengths, as like radiations from an incandescent light bulb or a star. Okay, radiation composed of a single wavelength is termed monochromatic. I already told you that. We're going to say it again. Monochromatic, one, single. When radiation from a source like the sun or other stars is separated into components, the spectrum is produced. Now, this separation of radiations of differing wavelengths can be achieved by passing the radiation through a prism. Okay, we're going to pass that radiation right through a prism. All right, so each component of the polychromatic radiation is bent to a different extent by the prism. This rainbow of colors containing light of all wavelengths is called a continuous spectrum. The most familiar example of a continuous spectrum is a rainbow, which is produced by the dispersion of sunlight by raindrops or mist. Now, most substances will emit light energy if heated to a high enough temperature, as is the case with forging fire. So it's glowing, right? It's letting off that light energy. We are in the same boat with neon gas. Neon gas similarly will emit bright red light when it's excited with a sufficiently high electrical voltage. But when energy is absorbed by substances, electrons within the atoms of the substance that may be excited to positions of higher potential energy farther away from the nucleus. Now, when these electrons return to their normal, or their AKA ground state, position energy will be emitted. Usually, some of the energy emitted occurs in the visible region of the electromagnetic spectrum, which is like your 300 to your 700 nano. If you're confused about that, we can click right back over to this one. There we go. We're talking about 300 to 700. So what I really want you to understand about this particular periodic table are electrons, specifically valence electrons, are important in determining how an atom interacts with other atoms. Now, the elements in a group have similar properties because they have valence electrons in similar configurations. So the elements on the periodic table are divided into categories. Not only is this system useful for finding elements, but many predictions can be made about an element based on its position in the periodic table. The arrangement of electrons in the orbitals of an atom is called the electron configuration of the atom. An aspect of quantum theory includes electron orbitals and shells within the energy levels of elements on the periodic table. Now, I just bring that to your attention because I just want to show it to you. So we describe an electron configuration with a symbol that contains three pieces of information. One, the number of the principal quantum shell, which is N, okay? Two, the letter that designates the orbital type, the subshell, or, L, and the subscript number that designates the number of electrons in a particular subshell. So I just want to make sure you saw that diagram, you can understand it. Now, this is one of my favorite tools for determining electron configuration. To determine the electron configuration for any particular atom, we can build, quote unquote, build the structures in the order of atomic numbers, beginning with hydrogen, which is number 1 at the very top on the left, and continuing across the periods. The periods run are rows, not columns, but rows. Beginning with hydrogen, continuing across the periods of the periodic table, we can add 1 proton at a time to the nucleus and 1 electron to the proper subshell until we've described the electron configuration. So electrons enter higher energy subshells only after the lower energy subshells have been filled to capacity durations of all the elements. Now, what is interesting is electrons fill the lowest energy atomic orbitals first, and I just said that. And these are your atomic energy levels. An electron configuration, here we go. An electron configuration, we're going to place those electrons into an arrangement around the nucleus that indicates their energy and shape the orbital in which they're located. This is simply a summary of the types of orbitals and how many electrons can contain them. Okay, how many electrons can actually contain them. Now this slide right here is an alternative method for determining the electron configuration. The filling order simply begins at a hydrogen and includes each subshell as you proceed in increasing Z order. You need 2 electrons to fill an s orbital, 6 electrons to fill a p orbital, 10 to fill a d orbital, and 14 to fill an f orbital. The order in which electrons are placed into orbitals is based on the order of their energy. This is referred to as the Aufbau principle. The lowest orbitals fill first and is summarized by the following chart, now that you've seen it. So for example, after filling the 3p block up to AR, we see the orbital can be 4s, which is Ka, followed by the 3d orbitals. How to write electron configuration. You're going to start with the shell number, which is your N, remember, and then you're going to follow that with a type of orbital. So the last thing you'll do is write the superscript, and that indicates how many electrons are actually in the order, or in the orbital. All right, so when we're writing some of the lower table configurations, the total configuration can be really long. Now you can use the previous noble gas. These are your noble gases. If we can get there, here we go. We have noble gases, okay? You can use your previous noble gas to abbreviate the configuration shown below. You just have to finish the configuration from the last noble gas element passes. So if you look at this one, this is lead. This is how long lead is. This is the shortened version. And what they did is if you find, excuse me, if you find lead on the chart, it's going to be right past, here we go. There's your xenon right here. So your xenon is right here. And so then you have, after xenon, so you put that in brackets, then you have your 6s2, this 1 and 2. Then you're going to have your F414, F414, then your 5D10, and then your 6P2, 612, and there's lead. That's how we find that on a chart, if you will. Using the same periodic table. Now, I use the same periodic table pretty much throughout the entire semester. I have several that are available that you can get out of D2L, and I am notorious for throwing around bonus points if you show up with what I've asked for. So make sure you're printing stuff out. So let's just look at an example. We have oxygen. Oxygen, 8 electrons, okay? Based on the order to fill in figure 4, these 8 electrons would fill in the following order, okay? 1s, 2s, you got 1s2, 2s2, and what is this? We have 2p, on and on, okay? So back where I told you, you're going to find that orbital periodic table very useful. That's going to be something you're going to want to print off and have available to you while you're working on this particular electron configuration worksheet. And that's all I have for the lecture. If you're struggling, make sure you reach out, make sure you attend tutoring, make sure you check out the tutorial center, ask your instructor. We're here to help, and good luck to you on this particular worksheet.